Everyone, we've been talking about a long time about where magnetic fields come from, the reason there is magnetism, and so now we're going to really dive into why things are magnetized. The reason for magnetism, we've said before, is moving charges. And in a current carrying wire, that makes sense because we have moving charges that create these magnetic field loops. We've seen them in the labs. For a permanent magnet, that doesn't really make sense. We've talked about this way back in the beginning, that for each atom there is some moving charge. If you look at the moving charge in terms of the spinning electrons or the orbiting electrons as they go around their central nucleus. So let's draw that one more time and discuss the reason for magnetism. So here's a very, very simple drawing of the atom. You can see we've got two positive charges in the middle, we've got some neutrons in there, and we've got the orbiting electrons. Again, I'm taking the electrons to orbit as if they were planets, and again, this is not exactly how they orbit. They orbit in probability clouds of where they should be based on their energy levels. What we're going to pretend is that, yes, the charges are orbiting like planets, and they also could have a spin to them. They could spin up, they could spin down, depending on which direction their angular momentum points in. What we talked about back in the last chapter was this magnetic dipole moment from moving charges. And to find the dipole moment, we took the current multiplied by the area of a loop. And this is how we create our simple motors. But now let's apply that to the simple electron orbiting the nucleus. So there we go. We have one proton with one electron. We've got a hydrogen atom. And we have this electron that is orbiting. That electron doesn't want to stay around the atom, and it has a straight line velocity and wants to leave, and it is a certain distance from the central proton. So it's got a radius, it's got velocity, and electrons have mass. So if you think back way to angular momentum, they have angular momentum in the form of RMV. The angular momentum is in the direction of the electron spin. So you put your fingers in the direction of the motion, you curl your hands, and you can see that for this one, the angular momentum of the electron is pointing into the page. So there is a direction for the momentum of that moving charge. Well, if I want to solve for the dipole moment of this little moving charge, I've got to dissect my mu over there. I'm going to replace current with the definition of current, which we said was charge passing through something per second, and I'm going to replace the area with pi r squared, since that is the area that that little charge moves around the circle. It's a flat area, it's not a surface area. Now, this time, the time it takes that charge to orbit once depends on how fast its orbital velocity is. So from orbital mechanics, we know that the speed to go around a circle is based on 2 pi r divided by the time. If I rearrange that and solve for time and put it down there, this is what you get. You get this, q pi r squared times v all over 2 pi r. And some things can cancel for us. Get rid of the pi's, we can get rid of one of the radiuses, and the magnetic dipole moment turns into qrv all over 2. However, since that charge has angular momentum, I do see r and v over here in the angular momentum equation. So I can get those two together and substitute out the RV I have in this equation, and what you finally get is that the magnetic dipole moment of a single charge orbiting its own nucleus is q times the angular momentum of that charge divided by 2m. Each charge there has its own unique angular momentum, and the dipole moment will point in the direction of wherever the angular momentum points. So in this case, we said the angular momentum was into the page, so the dipole moment is into the page, meaning there is a north pole created into the page because of this atom, and there's a south pole pointed out of the page. Now the simplest atom we have around is the hydrogen atom. So if we take the hydrogen magnetic dipole moment, we call it the Bohr dipole moment. 9.27 times 10 to the minus 24th amp meter squared. So in some of the problems in the homework, they will ask you to compare the dipole moment of the certain material you're given, whether it's nickel, iron, cobalt, and compare it to the Bohr magnetic dipole moment. So you're just going to take that ratio you find and divide. So how do we apply that magnetic dipole moment? Well, what we say is that if we can get atoms to align and have all their moments pointing in one direction, then we would say that that atom would be slightly magnetized, because you would have all the north poles pointing in one direction and the south poles pointing in the opposite direction. I am not a magnetic material. That means that my atoms are spinning in opposite directions, or most of my electrons are paired. But when you talk about different things like ferromagnetic materials, nickel, cobalt, iron, steel, those all have highly aligned magnetic dipole moments. Paramagnetic materials have partial alignment there, and diamagnetic materials do not like to be magnetized. Watch this video here from Minute Physics. He explains what we're talking about with this magnetic domains and these dipole moments pointing in the same direction. Once you finish that video, come on back and we'll talk a little bit more. So what he was talking about there with having these different dipole moments was explaining that inside a material, you can magnetize that material if it is experiencing a strong magnetic field. And we know we can create strong magnetic fields with solenoids. So let me show you an example. So let's say we have a solenoid here, and I put a metal into the solenoid. I want to create basically an electromagnet based on the material that's in there. So the magnetic field, the total magnetic field that's going to set up inside my solenoid here, is the applied magnetic field coming from the solenoid, which is Bunny, and the magnetic field from the magnetized material. That's what B sub n means. If you come back to the notes, in the notes here we can see that the magnetic material depends on the permeability of free space times the magnetization of the material. Well, how do we solve for the magnetization? Magnetization can be found by the X sub m, which we call the susceptibility of the material to be magnetized, multiplied by the applied magnetic field all over mu 0, which means if there's nothing in the solenoid, then there's nothing to magnetize. But when you put a material in the solenoid, depending on its susceptibility, it will become magnetized based on this value. This value can be found here in this table for different materials. You can see like aluminum has a positive susceptibility, while copper, bismuth, diamond, those things have negative susceptibilities, which means they don't like to be magnetized. But titanium, tungsten, those all are materials that do like to become magnetized. So I'm going to use what we have here for the magnetization and put that into our equation for the solenoid. So this is the magnetic field of the magnetized material. Remember, it's mu 0 times the magnetization of the material. What's going to happen here is I get rid of my mu 0, we get this. The net magnetic field is the applied magnetic field plus the susceptibility times the applied magnetic field. And that will show you that the net magnetic field is going to change if you put something inside the solenoid. So if I want to calculate how a magnetic field changes when something is put in there, what I could say is that when I watch a magnetic field change because I put something in the solenoid, I could see how the magnetic field strength is minus how it was without the material in there, and divide it by my applied field with nothing in there. That change in magnetic field over the applied field is another way that people find the susceptibility. They see how the magnetic field changes when a material has been placed in this external field. Another term that might come up in some of the problems is talking about the magnetic saturation of the material, meaning that when you put that material in the solenoid and it's experience a strong magnetic field, it's going to align all of its domains in the direction of the external field. And when it does that, you can solve for the saturation by calculating the dipole moment for that material and multiplying by little n. Little n, number of charges in a given volume. So that number there, you're going to have to use some chemistry and Avogadro's number to figure out how many atoms you have in a particular piece of metal, divided by the volume. That'll give you the little n, and you're going to multiply that by the dipole moment, or one of those unpaired electrons around those atoms. So like you can see here in the video, there are materials that have magnetic domains that do partially line up, but if you zoom out a little bit further, you're going to see magnetic domains pointing in opposite directions. To force materials to become magnetized, you have to make all their domains line up in the same direction. And to do that, you have to experience a very, very large magnetic field. This is a zoomed in view of your credit card. So that strip on the back of your credit card that you swipe when you want to pay something shows that there are magnetic domains with the magnetic dipole moments pointing in opposite directions along that strip. So if you put your magnetic strip on your credit card in the presence of a strong external magnetic field, it can realign these domains and completely mess up the code that has been programmed on that magnetic strip. In the case of diamagnetic materials respond opposite to an external field. They resist magnetic fields that go against them. Things like chromium or water even have high diamagnetic moments, which means if you experience a very, very large magnetic field for something that has lots of water in it, that object could float, like you're seeing with this frog or the strawberry. And if you had a really, really strong magnetic field, maybe you could even float yourself, since we're mainly water. But any of these domains can be ruined if we introduce thermal energy. So you can see right here that as we add thermal energy to the domains go and point in random directions again, and the material becomes unmagnetized. So like when I put the magnet next to a paperclip, paperclips are not magnetic until they feel a strong magnetic field. Then all the domains in the paperclip line up. And it might stay that way for a while, and actually that paperclip could then magnetize other paperclips. But if I pull the external magnet away, the domains do stay lined up for a little bit, but the longer I hold it, the more those atoms heat up in the paperclip. The more their domains are starting to shift back to their random locations, and the paperclip becomes demagnetized. But even a small bar magnet can be susceptible to large magnetic fields. The compasses are tiny bar magnets, and if you played around with them too much in the lab, you may have had them point in the wrong direction. They should be pointing towards north, but now they're pointing the opposite way. What did you do? You accidentally realigned the domains of the compass. And we can do the same thing with two permanent magnets. I have a device here called the magnetizer that you can put two magnets in, and I push a button. What happens is I shock those permanent magnets with a very, very strong magnetic field in the opposite direction. So I basically have two solenoids down in that chamber that are creating huge magnetic fields that go in the opposite direction and force all the domains to realign themselves. And now you can see that north and north attract while south and north repel. So I can do the opposite and force weak magnets to do what I want. The stronger magnet will always overpower the weaker magnet if you give it enough time or you expose it to a strong enough field. We can reverse what I just did there. With the magnetizer again, I can force the magnets to go back to the way I want, and now you can see north and north repel and north and south attract. So everything we've described here in this section has dealt with the idea of permanent magnets and how permanent magnets create magnetism because of their unpaired electrons and the orbit and spinning motion that they create. But that still doesn't explain the wire. The wire, yes, is moving charges, and we says it creates magnetism. But I'm going to leave a link here, and I would like you to watch this video for Monday. Watch Veritasium explain, using special relativity, how a current-carrying wire repels charges and creates magnetism. So enjoy the video, and we'll talk next time.